Hey everyone, welcome to this explainer by Forge College. I'm your host, and today we're taking the real-world network attacks we talked about in our last lesson on consensus security, and we're translating them into a theoretical engineering blueprint. We are diving into the origins of the Byzantine fault problem. If you've ever wondered what it actually takes to keep a decentralized network alive when some of the participants are actively trying to destroy it, well, you are in the exact right place. We're going to use this minimalist, patent-style blueprint approach today to strip away all the noise and focus purely on the mechanics of network survival. Here is our blueprint for today. We'll start with the messy town meeting, move into defining distributed fault lines, and run the equivocation simulation. After that, we'll look at engineering the defenses, calculate the magic ratio, and wrap the whole thing up with key takeaways and next steps. All right, Section 1, the messy town meeting. Let's look at distributed networks through a very human and, honestly, kind of chaotic lens. So to really understand distributed networks, imagine you're at a local town meeting trying to elect a mayor. In a perfect world, right, the worst thing that happens is someone falls asleep in the back row, or maybe they leave early because they left the oven on. But we are engineering for chaos here. What if an attendee doesn't just leave, but actually stands up, argues two completely contradictory positions to different neighbors, whispers fake vote counts, and literally forges the attendance sheet just to mess with everyone? They are actively tailoring their lies to deceive specific people in that room. So the real question becomes, how many honest people do you need in the room to drown out all that coordinated lying? Which brings us to Section 2, defining distributed fault lines. Time to map this messy human behavior into strict computer science terminology. Okay, so we need to define what a Byzantine fault actually is. And it's exactly that intentional deviation we were just talking about. It's a failure where nodes in a system don't just quietly crash and shut down. Instead, they behave arbitrarily. They might send out conflicting, totally inconsistent, or highly deceptive messages to different peers on the network. They're acting exactly like that rogue town meeting attendee. The term itself actually comes from the classic Byzantine Generals Problem, which basically asks, how can loyal generals agree on a battle plan when there are traitors right there in their ranks passing around fake orders? Now compare that to a basic crash fault. A crash fault is totally innocent. A node simply loses power or drops its Wi-Fi connection. It's the network equivalent of that guy leaving the town hall early because he left the stove on. Super easy to detect, right? Because they're just gone. But a Byzantine actor, they weaponize their participation. They pretend everything is completely fine while secretly poisoning the well of information, telling half the network one thing and the other half something completely different. Looking at this, it perfectly illustrates the three tiers of faults we actually have to engineer for. Crash faults, those just need simple timeouts or a quick leader election to fix. No biggie. Byzantine faults, on the other hand, where nodes are sending arbitrary messages, those absolutely require strong cryptography and strict protocols to manage. But malicious faults? This is where an actor lies specifically to maximize their own profit or to censor someone else. Those demand incredibly sophisticated, incentive-aware economic designs. You basically have to make the attack totally unprofitable. Okay, Section 3, the equivocation simulation. Let's run a concrete lab test on node agreement. So equivocation is really just a fancy, technical word for speaking out of both sides of your mouth. Let's take our blueprint and test it on a tiny 4-node permissioned blockchain. We'll call them nodes A, B, C, and D. Let's say node A is our Byzantine attacker. In step 1, node A proposes a brand new block, we'll call it proposal X, to nodes B and C. But then, in step 2, it turns right around and hands a completely different block, proposal Y, to node D. If the honest nodes are just following a simple, naive rule of accepting the first valid proposal they see, boom, we hit a dangerous split state. B and C validate X, D validates Y, and suddenly the network has fundamentally disagreed on reality. And this split, it entirely violates the core safety property of consensus. Safety means that all honest nodes absolutely must agree on the exact same block at any given height. When equivocation forces a split like this, it kicks the door wide open for double spend windows, where an attacker can literally spend the exact same digital money twice on two different versions of the ledger. Plus, it causes persistent network partitions, which essentially breaks the whole application. It's an absolute nightmare for any decentralized protocol. So how do we fix it? Section 4, engineering the defenses. Let's look at how we protect the network mathematically. How do we defend against this two-faced town meeting liar? Well, we deploy 3 main mechanical defenses. First up, cryptographic signatures. This gives us non-repudiation. An honest node can mathematically prove exactly who sent a message, meaning the liar can't deny it later. Second, public broadcast or gossip protocols. This lets nodes constantly compare notes with each other. If node B and node D gossip, they'll immediately realize that node A sent them conflicting signed messages. And third, monotonic counters, like sequence numbers. These are crucial because they stop adversaries from taking an old, valid message and replaying it out of order just to confuse everyone. Now, the philosophy behind these tools is actually fascinating. You see, they don't actually prevent a node from lying. If someone has a signing key, they can still totally sign a false statement. Instead, what these tools do is mathematically convert those arbitrary lies into detectable equivocation events. They literally force the liar to leave a cryptographic paper trail. Once the network gets proof of that contradiction, it can just ignore the bad actor or even slash their staked funds as punishment. We are taking a sneaky whisper and turning it into a loud, highly punishable crime. All right, Section 5, the magic ratio. Let's define the strict mathematical thresholds we need for consensus. So, there is a catch to everything we've just talked about. Remember our tiny 4-node lab test earlier? Just one bad actor was enough to cause a complete collapse. You can have all the fancy cryptography in the world, but if you don't have enough honest people in the room, the whole system still fails. And that brings us to the golden rule, the magic ratio of redundancy. N must be strictly greater than 3 times F. In this equation, N is the total number of nodes in your network, and F is the maximum number of Byzantine faulty nodes you can tolerate. Under partially synchronous network models, to guarantee both safety and liveness, your total nodes have to be strictly greater than 3 times the number of liars. This isn't just some abstract academic equation, guys. It is the absolute minimum engineering tolerance required. Think about it like this. If 1/3 of the room is actively coordinating to lie and confuse you, you absolutely need the other 2/3 to be honest, just to ensure you can reliably cross-check messages, securely gossip, and successfully outvote the deception. If F is one bad node, you need at least 4 total nodes to survive. If the bad guys control 1/3 or more, coherent majority agreement just flat out collapses. Finally, Section 6, key takeaways and next steps for building foundations. As you continue your programs and deepen your Web3 knowledge, keep in mind that these theoretical bounds are the bedrock foundation for all real-world protocol design. Our core philosophy today is exactly this. The adversary model defines the guarantees you can expect. If a protocol claims it's secure, you always have to ask, secure against what? A system designed to be safe under partial synchrony isn't magically going to stay safe if the network drops into total, chaotic asynchrony where messages are delayed indefinitely. The promises any protocol makes are really only as good as the threat model it was specifically engineered to withstand. In our next lesson on Byzantine fault tolerance mechanics, we're going to map concrete protocol patterns, things like leader-based replication, directly back to these exact fault assumptions. So when a new protocol claims it tolerates F Byzantine faults, you now know exactly how to evaluate it. You verify their network models, you check their message authentication schemes, and you rigorously analyze how they distribute evidence of equivocation. Until then, I want to leave you with kind of a provocative thought. We know equivocation is a threat, right? And we know we can mechanically detect a lie using digital signatures and gossip protocols. But if we can detect it, how would you design the economic punishments to make sure it never happens in the first place? How do you make the cost of the attack far, far greater than any possible reward? That intersection, right there between computer science and game theory, is where the real magic of Web3 happens. Think about that blueprint and how those incentives might actually work. To dive deeper into this subject, explore these economic questions, and master even more Web3 fundamentals, be sure to visit forge.college. There's a whole world of structured learning waiting for you over there. Thank you so much for joining me on this explainer. Keep questioning the mechanics of the networks you use, and I will see you in the next one.